Welcome to the morning session today. And today our first speaker is Hwajong from Seoul National University, South Korea. And he will talk about generalized Ogg's conjecture or Stein's conjecture, as the title says here. And yeah, over to you, Professor Wu.
Thank you very much. Thank you for introduction. Today, I'm going to talk about the generalized Ogg's conjecture. And as already can introduce this talk. And how to move to the next slide. Okay. First, let the n be a positive integer and x0 of n, as before, is modular curve over Q. And J0 of n is Jacobian variety, which is an abelian variety defined over Q. And by the model-based theorem, the group of rational points is finitely generated. And so there is some copy of G, and there is a finite abelian group, which is called the rational torsion subgroup of J0 of n. And our motivational question is, can you compute the rational torsion subgroup of J0 of n for any positive integer n? This is the motivational question in this talk. And well, historically, one natural candidate is the Cuspidal group, and a Cuspidal divisor of x0 of n is a divisor supported only on cusp, and Cn be the Cuspidal subgroup of J0 of n. This is generated by the images of degree 0 Cuspidal divisors of x0 of n. And by the theorem of Manin and Ribet, and these points, the image of Cuspidal divisor is always torsion, and therefore the rational points of Cuspidal group is contained in the rational torsion subgroup, and the rational points on the Cuspidal group is usually called the rational Cuspidal group. So our question is, can we prove this rational Cuspidal group is equal to rational torsion subgroup? And next question is, can we compute the structure of rational Cuspidal group? The Ogg's conjecture, when n is a prime, then in early 1970, Andrew Ogg computed the order of this Cuspidal divisor 0 minus infinity. And this is famous number is the numerator of n minus 1 over 12. And he conjectured the following. And for a prime number n, so the rational torsion subgroup of J0 of n is actually equal to the rational Cuspidal group. In this case, the two cusps are defined over Q, so this Cuspidal group is already defined over Q. So this is equal to the group generated by the image of 0 minus infinity, which is already a rational point. So in 1977, as you know, Mazur proved this conjecture, and his result is a formative answer of the first question. And because we know the structure of this one as well, this also answers the second question. The natural generalization of Ogg's conjecture is the following. So for any positive integer n, we have this equality. So rational torsion subgroup of J0 of n is in fact equal to the rational Cuspidal group of J0 of n. Based on this conjecture, can you compute this right-hand side? That is our next question. However, the structure of this group is not known for general n. So the one digression is can prove for abelian variety A over a number field K, the K mu infinity rational torsion point of A is finite. So this K mu infinity is a cyclotomic extension of K. And what is this group if A is J0 of n? Then one has this Cuspidal group is defined over some cyclotomic field, which is thus this one is inside of this rational torsion subgroup, Q mu and rational torsion subgroup. And can you prove this one in fact equality? However, there is some subgroup of this group from the Shimura subgroup. So this may not be equal, but maybe this one consists of this Cuspidal group and the Shimura subgroup. And this Cuspidal group and Shimura subgroup, the intersection between these two groups is at most of order 2. So this one consists of almost this Cuspidal group and some Shimura subgroup. And Yuan Ren studied this question in some cases, and he proved some of the result in that direction when n equal prime p. So let's come back to our original question. Let An be the group of degree 0 Cuspidal divisors on x0 of n. Then we have a tautological exact sequence, the AUN2 Cuspidal group, and this UN is here. UN is the group of modular unit on x0 of n modulo the scalars. And if you take the divisor, then this one become the principal divisor, and this quotient is isomorphic to this Cuspidal group. And can ask me whether this proof is mapped from the rational points of this AN to the rational points of this CN. And this map may not be surjective, but he asked me that this is surjective if you prove the first cohomology group of this one is 0, for instance. Then this must be surjective. So let's C of n be the image of this F in this rational Cuspidal group, which is called the rational Cuspidal divisor class group. And one may ask the following: these two groups are equal. So which means this F is surjective or not. And the second question, so we want to compute this right-hand side, but we don't know yet. However, the left-hand side, the structure of this group is unknown now, because last year I computed this group for any positive integer n. So if we prove this conjecture, then we answer the second question. So for instance, if n equal 2 to the r times m, where this m is odd square free and r is n mod 3, then the all costs of x0 of n are actually defined over q. So these three groups are equal. Therefore, we know the structure of this group in that case. But this is already new result, because this Cuspidal group we don't know except when n is square free. So we want to answer this question. So this is a variant of generalized Ogg conjecture, combining the previous two conjectures. And conjecture O, I don't know why this name, but just say maybe this is O. And for any positive integer n and a prime number L, we have these two groups are equal. Here, L to the infinity denotes the L primary subgroup of this abelian group. So if we prove this one for any positive integer n and any prime L, then this implies the generalized Ogg's conjecture and this question. So major theorem answers this conjecture O holds for any prime number n. So what is the known result for this case for composite number n? So Dino Lorenzini in 1995 proved that n equal p to the r for a prime number p is not congruent to 11 modulo 12, and L is another prime different from p. In that case, he proved this conjecture O using this, under this condition, Cuspidal group maps surjectively to the component group of the special fiber of the narrow model of G0n over Fp. And then there might be some rational torsion points mapped to the toric part. But he proved from some argument that this toric part, the point maps to the toric part must be comes from the Cuspidal group. So these two groups are equal under this argument, using this argument. But he cannot prove this, the map from Cuspidal group to the component group is not is surjective when P is congruent to 11 modulo 12. So he removed that case. So this assumption comes from that fact. And San Ling proved that this map is surjective, but he cannot handle R equals 3 case. But when R equals 2, he also handled the R equals 3 as well. And there is no progress after like more than 10 years. And then Masami Ota proved that when n equals square free and L does not divide 2 times GCD 3 and n. This means that when L is like square free, then for a prime L at least 5, then this conjecture O holds. And when L equals 3, then the conjecture O holds for square free integer n, which is not a multiple of 3, not divisible by 3. And I handle some case when n L equals 3 and n is 3 times p. And Yuan Ren proved that when L does not divide this number, then there is no Eisenstein primes, and therefore this Jacobian, there is no L primary subgroup of this rational torsion subgroup. And there is some known result when n is small enough. For instance, if x0 over n is an elliptic curve, then we know this conjecture holds. And some small integers, for instance, 125 or n equal 57 or 65, then this conjecture O holds. So there is no counterexample yet. Here is the main theorem in this talk. Let n be any positive integer not divisible by an odd prime L. Then the conjecture O holds for level n and this odd prime L. So we have this one. Furthermore, if L is at least 5, then the conjecture O holds for level NL. So this is some generalization of the work of Ota. And our proof, my proof is different from those of Lorenzini and Ling. So, and also when L equals 3, we remove their hypothesis. So, any questions? Now this, let me introduce the Eisenstein idea. Let n be a positive integer, and as usual, TP is the Peace-Heck operator, and WP is the Akin-Raynaud involution.
So, Hwajong, can I ask you a question?
Yep.
So, can you go to the previous slide?
Yes.
Yeah. So, when you answer this question, have you proved that this Cn is same as C subscript n on the way?
Yes. Okay, cool. This one is sitting inside between these two groups. We know that the left-hand side is contained in the right-hand side. In the middle, C sub n of Q of L to the infinity. So
Thanks.
yeah, they are between these two groups. So if you know these two, then you get the by sandwich, then the all three are same. So this is much more general result than the generalized Ogg's conjecture. Yeah, come back to the Eisenstein idea. So one may construct the two Hecke algebras. One is the mass BBT, is the usual Hecke algebra, the full Hecke algebra generated by all these Hecke operators. But some reason when Q, well, I should say P and Q, but when Q exactly divide the level N, then it is better to use the Archimedean involution instead of Hecke operators. So the basic reason is that in the Squarefree level, as Kenstock, the eigenvalue of TP operator is either 1 or P. So when L divides P minus 1, then these two eigenvalues are actually equal. So we cannot decompose this quadratic polynomial into linear one. However, WQ is an involution. So WQ square is always 1. And eigenvalue is either 1 or minus 1. So when L is odd, this plus 1 and minus 1 are always different. So we can factor this quadratic relation into linear one, which is useful. So that's why we use this bold P, this Hecke ring, instead of the usual one. So we consider the minimal Eisenstein idea in both rings generated by TP minus P minus 1 for all primes P not dividing N. We denote by I. This is a minimal Eisenstein idea. And why we study this Eisenstein idea? Because this group is actually modular over this TL, and the annihilator always by the Eichler-Shimura relation. And this, when L is odd, there is a natural injection to the special fiber and FP point or special fiber. And since Frobenius acts trivially on the rational points, this TP minus 1 minus P always annihilate this module. So naturally, this rational torsion subgroup, L primary part of natural rational torsion subgroup is a module over this finite ring. And also this L primary part of rational Cuspidal divisor class group is also a module of this ring. And we want to prove this equality as a module of this ring. So we will study this ring further. And I summarized what is the major strategy to prove this Ogg's conjecture. The first, he compute the order of this rational Cuspidal divisor class group, 0 minus infinity. This is done by Andrew Ogg. And next step is compute the index of this Eisenstein idea in this ring TL, say Y. And then another step 3 is compute the dimension of this étal part of the kernel of J0 of n, and say this one D of n. The maximal idea containing this Eisenstein idea is called usually Eisenstein prime in Kenstock, because he assumed that n is square free. But when n is no longer square free, then there might be another idea, Eisenstein idea, which is not containing this minimal one. So we say this special type of Eisenstein prime is called rational Eisenstein prime because it is related to the rational points. And step 1 in general is known by my previous work. And so we just omit this step. This step is well, elementary, but there's tedious computation. And this is the rigid part in general. And step 2 is the most difficult one. And step 3 is possible in some case. And since this module is annihilated by Eisenstein ideal I, this is easy to prove. And Y, therefore, Y is always multiple of X. So if Y over X is an adding unit, and D of M is 1 for any rational Eisenstein prime containing L, then we can prove this equality. This is basically major strategy. And I will show you in each step how this argument works. So the classification of rational Eisenstein prime is as follows. Suppose that M is the maximal ideal containing this Eisenstein ideal I. Then, well, we don't know the eigenvalues of TQ and WP in general, but the theorem tells that this eigenvalue is either 1 or -1 because it is involution. And because the residue field is of characteristic L, so it contains L. And also this TQ eigenvalue is either 0 or 1 or Q. So where this S2 is the set of the prime divisors of N, not in S1. So basically this S1 means the valuation of P, the valuation of N with respect to P is 1, and valuation of N with respect to Q is at least 2. So there's 1 and 2 denote and meaning that thing. And the proof of this proposition is not difficult. So if this maximal ideal is already, the first one is easy. And suppose that Q squared divide N. Then when M is Q nu, so it is related to Q nu form, then eigenvalue, because Q squared divide the level N, so eigenvalue is always 0. So therefore TQ in M. If TQ is not in M, then M is not Q nu, and so we kind of lower the level to level, kind of the levels is N prime times Q, where N prime is the prime to Q part of N. So this is kind of the somehow Squarefree level. So as in Katz's talk, we have this TQ minus Q and TQ minus 1 equal to 0. So eigenvalue is either 1 or Q. So that's this 0, 1 Q comes from. So before studying step 2, which is the most difficult one, and we deal with step 3. So M be a rational Eisenstein prime, then we have this dimension is always 1. So so the argument of major in prime level case works verbatim under the assumption L does not divide 2 times N. So we may replace N by NL as well. So roughly speaking, using the theory of Cartier operator in characteristic L, we can embed this étal part into this cohomology group annihilated by this maximal ideal N. This is the space of cusp form, and annihilated by M, so you get all the Hecke eigenvalues. So in this space, the Q expansion is just scalar multiple of some system of eigenvalues. Because we determine all the eigenvalues by the Q expansion principle, all cusp forms in this space are actually linear multiple of each other. Therefore, it is one-dimensional. Therefore, this one is one-dimensional. Because this is not 0, because Cuspidal group always belongs to this one, and Cuspidal group is of order L. So in the case of NL, so we also prove the similar result, but we compute the J annihilate the corner of J, corner of M in J, where J is the special fiber of the narrow model of this J0 of NL over FL. This is semi-stable. This one has semi-stable reduction. And when L equal at least 5, the dimension is always 1, you can prove. But however, when L equal 3, for some maximal ideal, we cannot prove this when dimension equal 1. That's why Ota's result does not work when L equals 3 and level n is divisible by 3. So now, for simplicity, Bn is the rational torsion subgroup of J0 of n. And first, we decompose this ring by some complete local ring. And since this TL is semi-local, we have this TL mod I is product of Tm mod I, where Tm is the completion of TL with respect to M. Accordingly, we can decompose each modules by this one, which is this M primary part of this Bn, and this is M primary part of Cn. So if we prove this M primary part, each M primary parts are equal, then these two groups are equal. So thus we suffice to show this M primary part of Bn is contained in the M primary part of Cn. So by step 3 and the Nakayama lemma, Bn, the M primary part of Bn is n most of rank 1 over this ring. So it suffices to show this M primary part of Cuspidal, rational Cuspidal divisor class group is free of rank 1 over this ring, then we get the result. So to illustrate idea, let us assume n is prime. So this is the proof by Mazur. So first, since WP square equal 1, either WP plus 1 or WP minus 1 in M, as before. And since there is no old forms, we have TP plus WP is actually 0 in the endomorphism ring. So Mazur proved that there is only one Eisenstein prime containing L. So like this Li and this WP plus 1, which is equal to TP plus 1, TP minus 1. So since L is odd and WP plus 1 is maximal ideal, so WP minus 1 cannot be an element of M. So this is unit in the complete local ring. So since this, we have this relation, and in fact, WP plus 1 is 0 in this ring. This is crucial in our study because we have the equality in the middle. And because this one, two are equal because there is only one maximal ideal, and these two are equal because this WP plus 1 equals 0, and these two equal because Tm is actually equal to TL. So from this one, we get this new one, which contains WP plus 1. This is very important. But however, in the Mazur's original paper, he somehow introduced Eisenstein idea always contains this element. But I think this is unnecessary. But anyway, you must prove this is the unique maximal idea in that case. So why this step is important? This question? Yeah, why is this step is important? Because this one, so this minimal Eisenstein idea, we somehow, there is some missing operators. For instance, in this case, WP. So however, this one contains all the operators. This is very important. So since any generators, TQ and WP are congruent to integers modulo I, so there is a natural surjection GL to TL mod I. So any operator in TL is congruent to integer modulo I, so there is natural surjection. So if this map is injective, there must be a cusp form which is congruent to Eisenstein series in characteristic 0. but this violates the Ramanujan bound. So therefore, there must be some kernel, non-trivial kernel, and therefore this quotient ring is isomorphic to some this ZL mod n times ZL. What is this integer n? This is called the index of this Eisenstein idea. And one can construct a Cuspidal divisor, in this case 0 minus infinity, annihilated by this ideal I, and which is the numerator of n minus 1 over 12 in this case, and compute this order, say m equal n minus numerator of n minus 1 over 12. From the natural projection, we get this m, order m is a multiple, this divides this number n. So n is a multiple of m. So this is how to get the lower bound of this number in general. This method works in general. However, the other part is difficult. But on the other hand, there is an Eisenstein series annihilated by I. And by the duality between the Hecke ring and the space of cusp form, this equality means over this ring, there is actually a cusp form whose eigenvalues congruent TP, eigenvalue AP is congruent P plus 1 in this ring. Basically, this cusp form, you may think about the eigenvalue is TP, and then TP is congruent P plus 1 in the quotient ring. So we can construct this cusp form. And after reduction modulo n, the Eisenstein series may be regarded as a modular form over this ring. So we get two different modular form in the coefficient in this finite ring. And then if you compare the eigenvalues, and they are all equal, so only differ by constants. So the Q expansions are differ by only constants, and there is no modular form over this ring when we assume that L equal at least 5, I should say more. There is no modular form over the ring whose Q expansion is the constant. So this constant term must be divisible by n. So by direct computation of the constant term of this Eisenstein series, in the major case, it is like n minus 1 over 24. So this constant term is almost equal to m. In that case, it's up to 2. And hence, this n over m is an L-adic unit. This is what we want. And this is basically the major idea to prove the Ogg's conjecture when at least under the assumption L equal at least 5. So note that in the duality, in the usual duality, for instance, the Katz paper in 1983, we usually use this normal Hecke, the full Hecke algebra, it's mass BBT. But however, in this argument, we use somehow the Archimedean involutions because of this stat. And in this case, we don't know. This does not make any difference because these two rings are equal. And in this prime level case, this is actually full endomorphism ring. And because we have this relation. So this finishes the proof. And what about the square-free case? This is an argument different from the original argument of the author, but we use crucially his result in many steps. So this is not much different from his original work. And let n be a square-free integer. And so the number of prime factor is t. And let's set this e is the t tuple of the plus minus 1. And let epsilon be the element of e. So this epsilon is given for constructing this new Eisenstein ideal. whose eigenvalues are specified. So, and then if you take generating L and this ideal, then you get a maximal ideal or the whole ideal. So if this is the whole ring, then we don't need to consider. And if it is maximal ideal, then there needs some argument. So as above, since this ring is local and blah 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 as before, you get this element is actually 0 in this complete local ring. This is very important. Therefore, a priori we get this quotient ring, but that is actually equal to TL modulo this new Eisenstein ideal. So instead of handling this Tm, we may just handle this TL modulo this new Eisenstein ideal. And also this one contains all the operators. So any generators are congruent to also the as above, the same argument, we get this isomorphism for some n. So now, as before, as like the prime level case, we can construct some Cuspidal divisor and Eisenstein series annihilated by this ideal. And then we can compute the order, we can compute the constant term, and we can somehow using some duality between this new Heckel ring and the space of cusp form, which is the difference from the Kant's duality, but the argument is like almost the same. But this new duality is proved by Masami Ota, and so therefore there is no like the cusp form in characteristic in mod L whose Q expansion is constant. So you get this constant term is divisible by the index. And this constant term, in fact, equal to the order. And so you get this module is free of rank 1 over this one. So this is basically the proof of Ota. And in the case of level NL, Ota somehow proved the duality between this ring and space of a regular differential. So this similar argument holds in the case when L equals 3 as well, without further assumption. So the Ota's result, so if you prove the missing theorem in Ota's result when L equals 3 is that this dimension is all étale part. The dimension of this étale part is 1 in that case. He cannot prove this one when L is a multiple of 3 and L equals 3. So I couldn't prove either. So now we move to the non-Squarefree level, which is the main contribution from me. And let's just write down this, like this prime decomposition of n is like the product of pi and product of qj. And here T is the number of elements in set S1, and U denote the number of elements in set S2. And here we assume Rj is at least 2. So this is somehow Squarefree. This is somehow we added in the previous discussion. So we need to consider somehow this part. So as above, let this E be the T tuple of plus minus 1, and epsilon be the element of this tuple, and define this new Eisenstein ideal. And then blah, blah, we want to copy the previous argument. And however, the difference from these factors. So we kind of lose some operator qj, tqj. So in this ring, So we don't know what is the eigenvalues of TQJ modulo this ring. So we cannot have this isomorphism. So nevertheless, we make just, because this QJ square, QJ square divide the level, the eigenvalue is somehow, if it comes from new form, then eigenvalue must be 0. So I consider this new Eisenstein ideal containing all this TQJ, which means eigenvalue is 0. So now this one contains all, all Hecke operators and Archimedean involutions are congruent integer modulo this ideal. So now we can prove this, there is an isomorphism like that. So this is very good. So as above, we can kind of construct some Cuspidal divisors and Eisenstein series, and we can prove blah, blah, blah. And then in this case, we don't need to use the duality. We don't need to have duality. We need duality, but in this case, the constant term of this Eisenstein series is already 0. So these two actually different modular forms has the same Q expansion. So by the Q expansion principle, these two are actually equal. So in that case, all the residue of this Eisenstein series must vanish in all other cusps. And then if you compute the residue at other cusps, then that must be, that is almost equal to the order of Cuspidal divisors. That's the argument in that case, in this case. Anyway, we can prove this Cn is actually, the M primary part of Cn is actually free of rank 1 over this ring. And therefore, we can prove these two M primary parts are equal. So as above, we can factor this module annihilated by this I0, where I0 generated by usual I and this TQJ, which we add. And then this one decomposes into the signs as before, like the Ota's case. And these two are equal by this argument. And therefore, we obtain this one and equal to this. This is, so far, this is a natural generalization of work of Mazur and Ota. So there is no some new result. This is just a direct or slight generalization of their work in the non-sequarefree case. However, main difficulty comes from how to obtain this result from this one. This one is annihilated by TQJ. So how to obtain this simplification? That's the main difficulty in the problem. And actually, I proved I proved this one is equal in like 3 years ago, but I couldn't get this direct implication. But my attempt is to decompose using the decomposition of Hecke ring. And then one may prove the result when n is divisible by n most square of the primes, which means Rj equal 2 for all j. And then also L does not divide Qj minus 1. This one means eigenvalue of TQJ operator is 0, 1, and Pj, and they are all different modulo L. So if these eigenvalues are all distinct, then we can kind of prove this TQ and blah, 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 and we can prove this result applying some idea, but this idea is like almost the same as before, but we cannot remove this assumption because if we assume Rj is at least 3, then the number of possible rational Eisenstein primes is smaller than the length of this one. So there must some violation in the argument. So we cannot get this result in that situation. So we need a completely new idea to prove this at least when L is divisible by some large power of prime. So here is my new contribution. And for any prime Q in S2, which means S squared divided the level, and assume that conjecture all holds for lower level. So kind of this is like levelaging. And if this one is true, then we have this one. The same is true for if you replace n by n times L. So that's the, so this proves our main theorem by induction. You get from the square-free level times some prime Q square, and then you get the level by the assumption plus O-test result. And then you can like kind of tiki-taka and you get build the older case by induction. So this is the main theorem. And the proof is not so difficult. And let Q in S2, so Q is a prime such that Q squared divided n. And first, we insist the following. If these two groups are equal in the lower level, then in level n, the TQ, after the operator TQ, these two groups are equal. So first assume this claim is true. Then we have the exact sequence. Applying the TQ, because TQ is linear, you get kind of this, this is corner of TQ and this is image of TQ. And because this one is inside of Bn, and applying this operator, the same is true. And you get the natural inclusion in all stat. And by 5 lemma, if this is true, which is true by the assumption and this claim, and if these two groups are equal, and then these first two are equal if and only if the middle is equal. So this is follows by 5 lemma. And since TQ commutes with other Hecke operators, we applying the same argument in the for all primes, you get this desired amplification. So it suffices to prove the claim. Let this be a the map from the pullback, and this is by push forward of the natural two degeneration map, which is usually denoted by alpha Q or beta Q. And then by definition, the TQ, we define that the pulling back of alpha Q and by push forward of beta Q, the composition of these two. And so since this Q squared, the divisor level, by direct computation, we get an alternative definition of Hecke operator. So basically, the definition of Hecke operator is pass through the level NQ, but you may just pass through this J0 of N over Q, kind of hit the lower level. And these compositions are the same. Therefore, also by direct computation, we have this Cuspidal group. If you push forward this Cuspidal group to the level N over Q, they are actually equal. This is you can prove in the level of divisor class divisor groups, not the image of divisor class group. So this you can prove that actually in the level of divisor group. So also you can prove the similar theorem if you replace n by nl or nl square. However, this may not be true when n is divisible by L cube. So this is a nice theorem. And since this map, the push forward is rational, so the rational torsion points of L power order, the image of this map is also belongs to the L rational torsions subgroup of L power order. So this is easy. So therefore we have, so this operator, this is by definition, by previous computation, this is alpha composition of beta. And because this inclusion, it is contained in this one and this. And by our assumption, this one is equal to this. And therefore, if you apply the pulling back, and you get the same, because it is already same. And then this one is by this theorem is equal to the push forward of Cn. And therefore, this composition is actually TQ, which means this TQ-Bn is contained in TQ-Cn. But however, this Cn is already contained in Bn, so therefore, these are actually equal. This completes the proof of claim and the proof of the theorem. It's a good time to start. Thank you.
Yeah, thank you, Professor Yu, for the wonderful talk. And may I ask if there are any comments or questions?
So you can prove that the Ital part is of dimension 1. So this is true for all n and all l?
No.
Okay.
The theorem is very difficult when L square divide the level. The point is that when L precisely divide the n, level n, so which in our slide is level n times L. In that case, we must study the kernel of M in the special fiber of the narrow model. But in that case, this is semi-stable model. We know what is the toric part, what is the abelian part, what is the component, and take the kernel, then you can compute it at most dimension 1. However, when L square divide the level n, for instance, in our case, our slide is level n times L square or L cube or something like that, then the most difficult part is the unipotent part. So if you prove the unipotent part, the kernel of M in unipotent part is trivial, then you can prove the dimension 1 result. But however, I don't know how to prove that. So there is some unipotent part. Unipotent part is somehow problematic.
Okay, any more questions or comments?
So Masami Ota was using some geometry. So you managed to just avoid them?
No, I used the same thing.
Okay, I see.
He managed to use geometry to obtain the duality.
Sure.
And he also somehow, in my argument, I just decompose everything and then construct some Cuspidal element and in each piece and then compute the order. But Ota didn't use this kind of argument, and he just used this whole package of Cuspidal group, and he used the result of Takagi of the order of this group. And this order of this group is bounded by, and this almost equal to the product of all the constant term of Eisenstein series that he used. So they are almost equal, so you get the result of the index. But I think my argument is much easier to his argument in some sense, because we don't need to worry about some kind of the congruence module, etc. that he is already
using congruence module.
Yeah, but anyway, my argument crucially use his geometric result in many
I
parts.
see.
Just I simplify his proof, I guess, but not the replacement of his proof in the Squarefree case.
Thank you.
Okay. Yeah, we still have some time. So if anyone has more questions or comments. If not, let's thank the speaker again.
Thank you very much.